Thomas, you're the first today. Can you hear me and see me? Oh, you're muted. Did you know that? All right, Thomas, can you hear me and see me? Oh, you said yes. I see it there. Okay, cool. Get everybody in here. I can tell the class is getting tired of this format. This is exhausting to use this Zoom all the time. I do say that people are, when fewer people are here each day, I do notice that the number of people checking out the YouTube videos goes up, which is fine. But I do encourage you to be here so you can ask questions as I go. Let's get all this stuff ready. All right, guys, so when we were last together, I was talking to you about these quadratic residues and the quadratic non-residues, and we start to have some tests for whether a number is a square or not. And I've tried to hint at how some of this, the business of knowing what's a square and what isn't, yeah, it has applications to things like cryptography and so on. To be perfectly honest, the main reason that I think number theory books always include this chapter is because it was very exciting to a teenaged Carl Friedrich Gauss. This is one of the first theorems that he became known for. He really was a teenager when he proved it, and he came up with multiple proofs in his life, and he convinced everyone else that it was a fun thing to work on. It's sort of at the boundary between what's clear and what's just kind of magical. So it's a fun theorem to pursue. So I'm going to work on that with you guys today, and I'll be able to get you the proof or most of the proof. Well, at least we'll be able to see how it works in the key cases that are of interest to us. So I actually prepared the slides in advance today. I'm hoping that I've got them visible. I tried to write a little larger, so we'll see if you guys can read. How visible is that for you guys? Can you read where it says P is an odd prime? Yeah, okay. Well, I have some options now. That's worse. Okay, that's definitely worse. Okay, so like I said, I would like to figure out quadratic reciprocity. I'd like to be able to tell whether or not a number is a square modulo something, modulo a prime anyway. And well, you know, there's ways that we can do it. You could obviously take all the congruence classes mod P and square them all, and now you know all the squares. But if P is huge, then you may not even be able to store all those data. We did have another way to test that. So I'll remind you first that we have the Legendre symbol as just a notation that tells us whether something is a square or not. And we write it like this. So it looks like a fraction, unfortunately. I think that's Legendre's fault for having such a bad notation. But it's either equal to +1 or -1, or it could be 0 if P divides A. But otherwise, it's +1 or -1, depending on whether or not A is a quadratic residue or a non-residue. whether it's a perfect square mod P or not. So quadratic non-residue. And one of the things that I have done with you is to point out that this will be the same as simply taking the number A and raising it to the power of P minus 1 over 2. And that is always something whose square is equal to 1. So it's this quantity is, I mean, except in this case, this quantity will always be either a plus 1 or a minus 1. And once we thought about using a primitive root and so on, we decided that getting the plus 1 or the minus 1 exactly coincides with what we already have. So I would like to find different ways to actually figure this out other than having to raise the number A to some enormous power. And well, there's various proofs of the main theorem. This is called the law of quadratic reciprocity. But, oh yes, so the one thing that we did have to get this started was this fact that this set of symbols is in fact multiplicative. So if we can figure out what to do for a couple of factors of a number, then we'll know whether or not that product is a square itself. So I say fact, it was a theorem, which is mostly obvious, but the fact that two non-squares multiply out to give a square, that's the non-obvious part. But I'll be using this when we start to do our examples. In fact, you can already see what this is going to mean is if I want to know whether or not 10 is a perfect square modulo P, it will suffice to know whether or not 2 and 5 are squares modulo P. So in that way, it'll kind of come down to just knowing whether or not any individual prime is a square modulo another prime. Some of those are easy to decide. If you wanted to make a decision mod 2, well, everything's a square mod 2 because everything is its own square mod 2. So it's really only the odd primes that matter to us. So by the end of the day, I want to get to a point where we could calculate this Legendre symbol where the numerator and the denominator are both primes. I'll know that the denominator symbol is going to be an odd prime, but I don't even know that about the numerator. I mean, it's a question to ask whether or not the number 2 is a quadratic residue modulo the prime P. So, in fact, that'll be one of the theorems we do first today. Actually, I do have to have one even more basic step, and that is the number -1 a square modulo P? And we've addressed that one. And I wrote it in the following form. I wrote it as it's going to be a plus or minus 1, but specifically it's -1 to the power of P minus 1. You see notations like this whenever number theory books are presenting this information. I wouldn't mind if you just stopped and thought about it a little bit and realized that this is telling you literally whether you're going to get a +1 or -1 by just talking about how P breaks out mod 4. So it's an odd prime is congruent to either +1 or -1, +1 or 3 mod 4, and in those two cases you know, the way we say this is you know the quadratic character of -1 mod P by just looking at how P itself reduces mod 4. All right, so if I ask you whether or not -10 is a square modulo P for some prime P, you'd need to write -10 as -1 times +10. I've already talked about deciding whether 10 itself is a square, and this will help you decide whether or not the -1 is a square. All right, so the next level of difficulty is to decide, well, what can we say about whether 2 is a square or not? And I have an answer for you, but I'm going to take you kind of slowly through the proof, which begins, of all places, with Wilson's theorem. So remember, Wilson's theorem was the statement that says when you compute P minus 1 factorial modulo a prime, you're definitely going to get a -1. Doesn't have to be an odd prime, but we only care about an odd prime. Now, I remind you that when we proved Wilson's theorem, I said, come on guys, you don't have to multiply the numbers in order. In fact, the clever thing to do was to multiply every one of these numbers by their multiplicative inverse. So 1 was by itself, p minus 1 was by itself, and all the others kind of got scrambled. On the other hand, you know, you might try multiplying them in order, and you get to some interesting things. And in particular, you might try sort of pausing halfway. If p is an odd prime, p minus 1 is an even number, so there is exactly a halfway point. Stop at p minus 1 over 2, and you'll get, well, p minus 1 over 2 factorial. Then there are the other terms that are being multiplied out to give you Wilson's theorem, but you'll notice that each one of these is mod p. It's the negative of one of the ones over here. P minus 1 is the negative of 1, p minus 2 is the negative of 2, and so on down the chain. P plus 1 over 2 and p minus 1 over 2 are negatives of each other mod p. So you can rewrite Wilson's theorem this way. You've got p minus 1 factorial, p minus 1 over 2 factorial once already. And over here, after you pull out all those minus signs, you'll have another p minus 1 over 2 factorial. So you have the square of that one multiplying out either a plus 1 or a minus 1, and I know exactly how many minus 1s there are. You got a single minus 1 for every one of these numbers. This is half of all of the invertible elements mod p. So p minus 1 over 2. Well, so we get some interesting conclusions out of this. I mean, when you combine them, put the minus signs in the right way, you first of all have a way of computing the square of this particular factorial. It's something, you don't really know why that's of interest, except you do notice that you get a plus 1 or a minus 1, and you can even tell whether that is a plus 1 or a minus 1, depending on what p reduces to modulo 4. So when p is 1 more than a multiple of 4, what have you got? In that case, this is 2 more than a multiple of 4, so this exponent is odd, which means you have just calculated a square root of negative 1. I now have a formula for what a square root of negative 1 might be in this case. We've previously proved, using primitive roots and so on, we proved that in this case there is a square root of negative 1. I mentioned that last time, but now I actually have a formula for it. I also have something to say in the other case, when p is 1 less than a multiple of 4, well then the p plus 1 is a multiple of 4, so this exponent is even, and I have a plus 1 here. So whatever this p minus 1 over 2 factorial is, it's a number whose square is plus 1, and the only two square roots of 1, modulo any prime, are always plus 1 and minus 1. It is an interesting question to look at all the primes that are 1 less than a multiple of 4 and calculate this factorial on the left-hand side and see when do you get a plus 1 and when do you get a minus 1. There is a pattern in there, but it is, I can only call it extremely subtle. It depends on something called the class number. So it exactly is whether this is a plus 1 or a minus 1, I will only say that it depends on the quantity called h. It's called the class number of this field. And I mentioned this field for you because we have discussed things like this much earlier in the semester. When that p is replaced by a 1, then this is the notation that we use for those Gaussian integers. I'm sorry, I should, I guess I should have a z in here. Anyway, for the Gaussian integers, there is a number that you compute from the Gaussian integers that reflects the fact that you do have unique factorization in the Gaussian integers. This number h that corresponds to that kind of a situation is h equals 1. But when you don't have unique factorization, and that's what we saw in the cases of, I think we did this example, didn't we? We adjoined a square root of negative 5, if memory serves me correctly. That is an example of a setting where you do not have unique factorization. You guys might remember my 2 factorizations of the number 3. And basically, it's just the fact that there are 2 and only 2 factorizations. That's kind of what's behind the calculation of this thing called the class number. That's not a 1 in this case. And in fact, the fact that one of these is odd and one of them is even that's related to how one goes about calculating the circumstances under which you get a +1 and the circumstances when you get a -1. So that's way deeper in the number theory than we're going to go in this course. But I wanted you to see that these are the things that the natural questions that people ask, and sometimes the natural question to ask has a very complicated answer. A little sidebar here, I couldn't remember the exact relationship between these factorials and this number ACE. It's called the class number. So I decided I would look it up, and it's hard to look up a formula like this. But what I did know, an easy way to look up is I calculated the first few examples of the primes that are congruent to -1 mod 4, calculated the factorial, and looked to see the occasions when I did get a +1 and when I did get a -1. And that gave me two separate sequences of integers, primes actually. Well, you guys should learn about what's called the OEIS, and that stands for the Online Encyclopedia of Integer Sequences. Anytime you want to figure out if there's a pattern to a bunch of whole numbers, a sequence of whole numbers that you're looking for, just go to, I believe it's oeis.org, or you can even just in your Google search bar, what I did is I just typed in the letters OEIS and then the first few values of P that gave me a +1, or I think maybe I plugged in the P's that gave me a -1. And sure enough, Google is smart enough to go consult this database, and it comes back and it says, oh, you must mean the following sequence. And then it describes the terms of the sequence, and it gives you links to places online where you could learn more about this issue or any other issue that pertains to your favorite sequence of whole numbers. All right, so all of this was, besides the fact that I wanted to give you guys some fun background on some of the issues related to things we've already discussed, I did want you to see that the p-1/2 factorial turns out to be an interesting thing to consider in the context, at least, of Wilson's theorem. And do keep an eye on this part too, that when you start looking at the products of the bigger numbers, I shouldn't say bigger and smaller when you're working mod p, but you know, there's the numbers that they're represented by actual integers that are small, and these, either you have to look at, you call these numbers big, mod p, or you call them negative mod p. And those words don't really quite make sense, but that informally, we're talking about half of the residue classes as being small, or call them positive, and then the other half, you could either call them large or call them negative. Now, I need that when I start working on the quadratic character of the number 2. So I said at the beginning somewhere, I think I've already lost it, that I was going to try to figure out what, oh yeah, here, I wanted to figure out whether the number 2 is a square mod p or not. So I've got a method to figure it out, and it's kind of weird, but it's fun. And this actually was one of Gauss's proofs, and a similar technique you'll see me use for a variant of, it might have been the same proof of Gauss's. People manipulate the parts of the proof. So what have I done here? First of all, I've started to introduce a funny notation you might have seen before. You know that the exclamation mark is used for factorials, and it means you start multiplying with the integer shown here, and you keep decreasing by 1 until you get down to 1, and then you stop. People use the double factorial to mean go down by 2's. So you start with p-1, and then subtract 2, and subtract 2 again and again and again. And you will end up either when you get to the 2, that's if you start with an even number. Of course, if you start with an odd number, these would all be odd numbers, and you would end with a 1. But since today p will stand for an odd prime, my p-1 is an even number, and I've got here a large collection of even numbers multiplied together. Now, there's a couple of ways that I could relate this to just an ordinary factorial, or at least mod p, I can relate it to ordinary factorials. One is the way that you already see me doing here. If all of these factors are even, let's just pull out a factor of 2 from each one of them. So there's exactly, if the biggest number is p minus 1, then there's half that number of integers being multiplied together. So there's that many 2's, p minus 1 over 2, 2's. And when you've pulled those factors out, then you just have p minus 1 over 2, p minus 3 over 2, that's the next integer down from this, and so on and so forth. So this is exactly the factorial that I was discussing on the last page. So yeah, here I wrote that out for you. All of these even numbers are twice something, and those, if these numbers go down by 2, then these other factors here go down by 1s. So yeah, so I wrote that out. So this one is exactly 1 less than the one that came before it. So pull out all the powers of 2, and then you have a factorial left over. So that's one of the ways that you can compute this, this double factorial thing. To kind of relate to what I was doing with Wilson's theorem a minute ago, let me also point out that you can write p minus 1 double factorial by saying, well, it's all of p minus 1 factorial times, divided by the things that you didn't include. So what was missing would be the p minus 2, the p minus 4, and so on, up to, or down to, let's see, there's the 5 and the 3 and the 1. So that's what it is as integers. I mean, this is an integer in the denominator that divides that integer. Or maybe it would be better if I didn't have a division symbol. I spoke to you guys how some of you got trapped with the idea of a division mod p. So let me write this same equation through as a product instead of a quotient. And that's, so that comes out to the p minus 1 factorial. But the missing terms in here are all the negatives of the ones that I had before. And the mod p, they're the negatives of the ones that I have before. This is congruent to -2, this is congruent to -4, and so on. This is congruent to the p minus 1. So this is the same kind of thing as I was just discussing with Wilson's theorem. You have here a large number of factors of -2, it's -2 to this many power, times everything else that remains is, oh, I'm sorry, yes, it is exactly what I said before. In other words, this, what you see here is, it's -1 to the p minus 1 over 2 times this p minus 1 double factorial a second time. And yes, I just showed you how I could simplify that over here, but I meant to say that it's this, that the missing factors from the p minus 1 factorial, the factors that are missing in the p minus 1 double factorial, they are exactly going to be plus or minus another copy of the p minus 1 double factorial. All right, so let's just focus on the p minus 1 double factorial. It's all these even numbers. So you have a power of 2 multiplied by the factorial that I was talking about with Wilson's theorem. Now, my next observation is that if I take if I take all the numbers from 1 to p minus 1 and I double them, like you see here, from 1 to p minus 1 over 2, and I double them like you see here, then first of all, I know that these are all going to be distinct mod p. If the double of something is congruent to the double of something else, since I'm working modulo an odd prime, 2 is invertible, and I conclude that x will be congruent to y. But I also know that none of these is congruent to the negative of any of the other ones that's in here. Because if you take the doubles of any of these small numbers and they are negatives of each other, well, as in the previous line, you could factor out or cancel the factor of 2. You can multiply both sides by 2 inverse. Moving things over to the same side, you would be just saying that the two small numbers add up to something congruent to 0. But each of these small numbers is bigger than 0, and less than p over 2. So their sum would be greater than 0 and less than p. And so there's no way that it could possibly be congruent to 0 modulo p. The consequence is that when I look at all of these numbers mod p, if I take the big ones and write them as the negative of something and leave the small ones alone, so that's the same kind of thing that I had done in this illustration. I left the small ones alone, but I write the big ones as the negative of something. Then, okay, you'll have a bunch of negative signs over here, just positive signs over there, but you will just see small numbers, and you might think that they get repeated, but this argument shows that they don't. None of these big numbers, when you write them as the negatives of small numbers, you'll never get the negative of one of the small numbers that you already have over here. So thinking about these residues mod p and changing the big ones to small, you end up with a distinct collection of numbers that are all small, which means all you have in here is the product of all the small numbers. All the numbers from 1 to p minus 1 over 2 have to be in here because there's exactly p minus 1 over 2 numbers, and after you make them small, they're all distinct. So since there are only p minus 1 over 2 small numbers in the first place, I must have listed them all here in some order. In fact, you can see I've drawn a graph of this process of doubling for you. When you take one of the small numbers between 0 and p minus 1 over 2 and you double it, well, then you get something between 0 and p minus 1. And then when you take the larger half and you start doubling them, well, when you reduce those mod p, then you have to sort of start over again. But when you just double the small numbers, some of them stay small and some of them are now big. And yet, if I write every one of these big numbers, they're more than half of the p minus 1. If I write them as the negatives of a small number, I won't be using any of the same small numbers that I already had. All right, if you keep track of the minus signs, here's what I've just decided. This p minus 1 double factorial, I've already calculated it in one way, but this new way of looking at it says, you've really got all of the numbers, all of the small numbers multiplied together once and only once. There's no repetitions in here. You have, however, picked up a lot of minus signs. Exactly what will happen is every time you took one of these small numbers and then you doubled it, if you got something that became big when you doubled it, then that kind of forced you to write it as the negative of something small, and so you'll pick up a minus sign for that. So here's where you are now. The p minus 1 double factorial has now been written as the p minus 1 over 2 factorial times the exact number of minus signs that I need is the exact count of the small numbers that I doubled to make this, which became large in the process. They were the numbers that got to be so large that I wanted to replace them with themselves minus p. And here's what small and large mean. I started off with only these small numbers, so x had to be less than halfway through the list of possibilities. And then I only had to throw in a minus sign on those occasions when doubling the number gave me something that was more than halfway. So it was only the number of minus signs that were kind of involved in this section of the product. All right, so I will pause there. Now I'll tell you that I'm doing all of this with the number 2 because 2 is small and I can draw my pictures more easily. We'll be able to do the calculations. But actually, everything about this proof is going to work just fine if I take some other some other residue mod p other than 2. I'll go through the review with you in a few minutes when we try replacing the 2 with something else. But this is the pattern that we're using here. We're taking all the small numbers, meaning from in the left half of this picture, and we're multiplying them all by the same thing, which obviously just gives me a huge factor of that number. And then what's left is, well, all those numbers that I started doubling. They were the numbers from 1 up to p minus 1 over 2. So I stopped there, and then I did this separate analysis that I said, well, you know, when you scaled all the small numbers, you didn't only get small numbers. Some of them were big, and when you subtract p, you can make them be small, but then that will introduce a minus sign. And the number of minus signs is shown right here. It's the number of small x's that got big, that big, when you doubled them. Okay, so here's two different ways to compute that p minus 1 double factorial. They both have this p minus 1 over 2 factorial in them. And we know that that quantity is invertible because it's not a multiple of p. In fact, my little preparatory remarks today said that that's either going to be plus or minus 1 or a square root of negative 1. So if I set these two expressions for p minus 1 double factorial equal to each other, and then cancel this invertible number, mod p, what I've just decided is that this power of 2 is congruent, mod p, to this power of negative 1. Here it is, I just said the same thing. Here's the two expressions. Both of these are equal, or one of them is equal to the p minus 1 double factorial, and the other is congruent to it. So they're congruent to each other modulo p. So cancel that, and then use the fact that, as I reminded you at the beginning of the hour, that exact power of a number like 2 is exactly the value of the Legendre symbol, 2 when read mod p. So I will use the Legendre symbol instead of that power of 2. So here's my left-hand side is the Legendre symbol. It's a plus or minus 1, and it's whatever that power of 2 is. But now I know that that power of 2 is congruent to this number, which is, of course, obviously also a plus or minus 1. So that seems like it lines up. All right, well then all that remains is, if you want to know whether this Legendre symbol is a plus 1 or a minus 1, you just have to figure out what is this number of x's. Exactly, I'm asking you to count how many of these small congruence classes, mod p, stayed small when you doubled them, and how many got big. And I mean, I know you know the answer, sort of. Obviously, half of them stayed small and the other half got big. But when you nail it down, you realize it's not exactly half. I mean, it can't be exactly half because this might be an odd number of candidates. So here, I worked it out for you. It depends on, well, here, let me just hide that much for a second. Obviously, if you want to have the number x be considered small in the first place, it has to be smaller than p over 2 instead of larger. So that's one of the two inequalities that you need to satisfy. And I guess I could be writing p minus 1 over 2 or whatever, but since p is an odd prime, this is clearly not a whole number, so the less than symbol can be less than or equal to, it won't change anything. Now, when you say that doubling it suddenly gave you a number that I'm considering large, that simply means that doubling it gave you a number that's more than p over 2, and I know you guys know how to divide by 2. So here's the inequality the other inequality you need to solve. So clearly, it's about a quarter of the residues mod p that are between a quarter of a p and half of a p. But to figure out the number exactly, you have to look at the congruence class of the prime p modulo 8. Because watch what happens. If you know that 8 is of the form, x is of the form 8n plus 1, then your inequalities go like this. X needs to be between 4n plus a quarter and 2n plus a quarter, and this one is 4n plus a half. Well, of course, x is supposed to be a whole number, so saying that it's more than 2n plus a quarter means that it's actually at least 2n plus 1, and to say that it's less than 4n plus a half means that the biggest it can be is 4n. So how many integers are there in this interval? Well, you take the biggest minus the smallest. Don't forget you have to wait, you have to.
We're looking at P modulo 8, right?
P, yes, thank you, sorry, yes, that should have been P modulo 8. Good call, thank you. So then it's the x's, yeah, I got the inequalities are on the x's. I think I just realized too, I did the wrong thing here. So how many integers are there between 2n plus 1 and 4n? You subtract the big minus the small. Oh no, I did right. And then add 1. You know, it's fence posts and fence sections. So it's that number minus that number plus 1. So that gives me exactly 2n in this case. When p is 3 more than a multiple of 8, then that becomes a 3/4, then this becomes a 3/2. So my lowest x doesn't change, but now my biggest x, you can see I'm allowed to go 1 greater. And so the number of x's in this interval is different. It's 2n plus 1. And well, I'll let you go through the calculations in these two cases. You pick up an extra one here. 5/2, yeah. You pick up, that goes up by 1, and this goes up by 1, so nothing changes in this column. And in this case, that one doesn't change, but this one does go up by 1, so you've got an additional one here. So I know the number of x's the number of small x's that get big when you double them. It's always about 1/4 of p, but you know, to say it precisely, it's this number. And the key fact about this is that now it's going to be even in this case and that case, and odd in these other two cases. There it is. So, and that even and odd is the relevant thing, because that number that I was just computing is the exponent that I'm going to put on -1 to decide whether this should be a +1 or a -1. So that does it for us. In these 4 cases, I now know whether this Legendre symbol is going to be a +1 or a -1. And here's the way I might summarize it. X is equal to +1. It's +1 in these two cases when you are 1 more or 1 less than a multiple of 8. And if you're further away from a multiple of 8, then 2 is not a square modulo p. So I had a similar thing for you before for the Legendre symbol of -1. And in that case, what mattered is how, I'm glad you said something. Now I have to keep checking here. What mattered was how the prime fell modulo 4, but now we see we have to look just a little further and look modulo 8 to decide whether 2 is a square or not. And I told you people do like to write the quadratic character for -1 rather than writing it out in a 2-line formula like this, which, let's face it, this is actually a little easier to read, but it takes more space. People like to write it out in terms of exponents. There's a way to do that with this situation as well. It turns out if you take p squared -1 over 8, then that gives you either an even number or an odd number, depending on which of these two situations you're in. So this is a compact way of saying the same thing. But you get the right conclusion. You get the, you decide whether or not 2 is a square modulo p by looking at how p falls modulo. In this case, it's 8. Actually, I can write it this way. This modulus here where I'm looking is it's 2 times the a that I'm testing right in here. So when I get to well, in a minute, I guess I'll run through a little bit with you what happens when we try to decide on the quadratic character of 3 modulo p. And the answer is going to be that we're going to need to know how p falls modulo 6. I guess this is a 4. You'll see. So for odd primes, we'll have a similar kind of calculation, but it won't be mod 4 or mod 8 either. Instead, it's going to be modulo 4a. So when I want to decide on a quadratic character of 3, I'll need to be looking at p modulo 12. All right. So this is a more complicated one than the one we had before, but we're building up our repertoire of what we know about which things are square modulo p. And this proof Well, it'd be a pity to get all that proof and use it only for deciding on this particular Legendre symbol. So I'm going to state this as Gauss's lemma and then kind of run quickly through why we've already proved it in the situation that we just looked at. So Gauss says it this way. He says, look, if you want to decide on whether or not your number A, which is co-prime to P, is a quadratic residue or a quadratic non-residue, it's, you know, plus or minus 1, and I'm going to write it, Gauss says I'm going to write it as minus 1 to an exponent. Of course, all you need to know is whether that exponent is even or odd, like we just did. But specifically, he counts it as it's the number of small x's that become large when you multiply them by your number A. And the example we just did was A equals 2. I gathered together all the evens mod P. You get all of the evens mod P by just doubling the small numbers mod P. And, well, some of them stayed small and some of them got big. And you count the ones that get big, that's your exponent. So let's read through the proof again and see how this works. Now, my picture would be different. If you looked at the tripling function, mod P, obviously you're going to have 3 zigzags like that. And so stopping exactly halfway through gives a more complicated picture. I won't even attempt to draw a picture that applies when the number A is pretty big compared to P. It starts to look like just kind of a random bunch of jiggles because the slope is so great that you very quickly bop down to the lower edge. Nonetheless, if you stop just looking at the picture, you could say, okay, well, I will look at this product here. I will take all of the small numbers. Now, small will always mean the lower half of the residues mod P. Take them all and just multiply them by whatever your number A is. And obviously, you're going to get a lot of factors of A. You'll get exactly that many factors of A, which is great because that's the exponent on A that you need when you want to compute the Legendre symbol. So we're working the Legendre symbol into our calculations on purpose. And once you pull out all those factors of A, what will be left will be this P minus 1 over 2 factorial. That will not change. That will always be the same thing. Now, the other thing to realize is that when you took the number A and you multiplied by all these small numbers, well, you know, some of them stayed small and then some of them got big. Oh, and look here, we have another bunch that's staying small again. So you get a kind of an erratic pattern of some of them staying small and some of them staying big. Nonetheless, what we said earlier is true. Every time you get a fairly big number, suppose you take this small number x and you multiply it by A, and you get now something that's big. Maybe A times x turns out to be, I don't know, P minus 4. Well, in that case, you just say, well, that's congruent to negative 4, which is to say you'll pick up a factor of a negative 1 times a 4. And that negative sign, you'll pick up one of those negative signs every time your A times x is in the big half. What you'll be left with, of course, well, now these will be small numbers. You'll have all these minus signs, and then you'll have some small numbers. But the reasoning that I use down here says, you know what, even though you've got things all jumbled up now, none of the small numbers that you have as a multiple of A is ever going to match a different small multiple of A, because you could just divide through by A. A will be invertible. And on the other hand, none of these negative numbers, the numbers that become small by throwing in the minus sign, mod P, none of them ever matches the A times a small number either, and it's the same kind of reasoning that I used here. So you get no repetitions among all of these small numbers. You took exactly that many small numbers, you multiply them all by A, and lo and behold, all you've got is exactly that many small numbers again, and they're all different. And so their product, oops, where'd it go? Oh yeah. So their product turns out to be all of the same small numbers multiplied together, but with a whole bunch of minus signs. Namely, it's all of the small x's that you have, which become large when you multiply them by A. And that's how Gauss stated his lemma. All right, so we could go through with the congruence classes, figure out what are the primes for which the number 3 is a square. And so what you have to decide is what are the values, the small values of x, less than p over 2, for which 3 times x, when you reduce it mod p, turns out to be bigger than half. And you get a few inequalities, and there's a few things that you can check. And what you will discover is that it will be a range of, it'll be about half of the possible x's that you're concerned with. But exactly how many will depend on how p falls modulo, actually I don't remember if it's modulo 3 or modulo 6. Well, let's find out. So let's see, we need to have an x that's between 0 and p over 2. And I'm going to look at this, trying to decide whether or not 3x, when you reduce it modulo p, is actually going to be between p over 2 and p itself. So when I say this, I mean that 3x itself is either between p over 2 and p, or 3x is between, see if I reduced it by a p, then I would get here. So it would be 3p over 2 and 2p. Now, it won't be any bigger than that, right? If you, oh, let's see, I guess for 3, we're already done here. Since your x is less than p over 2, 3x can't be that big. In fact, I see now there aren't any. So in principle, this list would have continued, but I'm already done. There's no additional x's that will satisfy this inequality after you this kind of an inequality after you reduce mod p. Reducing mod p can only mean subtracting a single p. So this one is pretty easy. For when you want to get the quadratic character of 3 modulo p, then it's a question of counting the x's that are less than p over 2, the positive x's that are less than p over 2, but more than p over 6. P over 2. Yeah. So those are the x's that satisfy this inequality, one inequality. I just have to count the x's that are in there. And as in the previous case, you'll see that what happens kind of depends on how the prime breaks down. I guess modulo 6 will be enough for us to test it. Usually you would check modulo 12, but in this case we'll have some repetitions. Just mod 6 is enough. So let's see, all of your primes mod 6, they have to be congruent to either 1. You can't have a p that's congruent to 2 mod 6 because then p would be even. Can't be congruent to 3 mod 6 because then it'd be a multiple of 3. Can't be congruent to 4 mod 6 or 6 mod 6 either. So the only other possibility is that p is 1 less than a multiple of 6. 6n plus 5. So in this case, in the top case, we know that x has to lie between. So 1/6 of this is n plus 1/6, and less than half of this would be 3n plus a half. So really that says x has to be at least n plus 1 and at most 3n. And so the number of x's is going to be 2n exactly. So the number of x's is exactly 2n here. And in the opposite case, then the x's have to be more than n plus 5/6, which means they're at least n plus 1, and less than or equal to, let's see, it'll be 3n plus 2.5. So you could go up as far as 3n plus 2. And now the difference between these two is 2n plus 1. 2n plus 1, adding 1 for the endpoint, that's 2. Wait, I have a sign error here. Something is wrong, because those are both even, and one of these cases is supposed to give me something odd. well, let's try it here. What happens when you work modulo 5? So the numbers you want to double are 1, 2, 3, sorry, triple are 1, 2, 3, and 4. So the residues will be 3 in this case. 3 times 2 is 1, mod 5. 3 times 3 is 9, which is 4. 3 times 4 is 12, which is 2. So when I reduce things, when I try to make the big ones become small, it's only this one and this one that are big. So that should give me 2 minus signs. The product of these 4 triples of numbers oh, I'm sorry. I'm only supposed to go halfway. When I triple these 2 numbers, that one became big, that one stayed small. When I make this one big one small, I treat it as a -2. So the product of the small numbers is now 1 times 2. It's the p minus 1 over 2 factorial. I picked up a single minus sign, which is an odd number. Why did I not get an odd number? The small numbers,
Shouldn't we have the inequality where x is greater than p over 6 but smaller than p over 3, maybe?
no, because it's all about, small always means compared to p over 2. So I took the small numbers, all of them,
Right. Yeah,
and then when I tripled them, so now I'm looking at 3x. The question is, is the 3x greater than or less than p over 2? And already here, when x is equal to 1, that's less than p over 2, but the triple of it, 3x is 3, that's more than p over 2, which is because this x is more than p over 6. Of course it is. X is 1, and p over 6 is 5/6. So that was, it was in the interval, a single x that was between p over 6 and it was less than p over 2. So since this is a prime that's 6 times 0 plus 5, the range of x's is I should have been able to go from 1 up to, oh, this is prime.
I mean, don't we consider the intersection of the two inequalities on top left corner? That's what confused me.
Yes. It's the top left corner, although when I say top left, I mean, I didn't draw my, I was trying to schematically draw a line with a slope of 3, but really, at the very first instance, we already have a congruence class of 3, which is in the top half. And then when we doubled this one, we already had to wrap around. See, I told you that picture that I drew, I had to draw it only for a equals 2, because that's a nice small number, and I could draw a line with a slope of 2. But in this picture, already having a slope of 3 puts the very first one of these, it's a small number that when you triple it, it has gotten big. The big numbers are 3 and 4, by the way, and the small numbers are just 1 and 2. So there's 2 small numbers that I have to triple. The triple of one of them was big, and the triple of the other one was small. So this one was, the number 1 snuck in because it is greater than or equal to 1, and 2 snuck.
What I meant is, on one side we have x greater than 0 and smaller than p over 2, and
Correct.
On the other hand we have x greater than p over 6 but smaller than p over 3. So when we combine these, shouldn't it be between p over 6 and p over 3?
Oh, I'm sorry, you are correct. Yes, I still need this inequality of x is less than p over 2, but you are correct. I should have said here, I didn't follow through with what I wrote. You are correct. To have an x that's, for which the triple of x is large, says that 3x is between p over 2 and p, or as I said, you could have continued down lower if it was possible to do so. But in now, I forgot about following through this inequality. Having 3x be more than p over 2 does mean this part, but it also means that x has to be less than p over 3. Thank you. That's what I was doing wrong. All right. Okay, so when x is of this form, then to say that x is less than p over 3 means that x has to be less than 2n plus 1/3, 2n plus 1/3, which means that x, in practice, that means x can be at most a 2n. There we go. And so there will be no x's that make this true in that case. Whereas in this case, when n is 6n plus 5, then the inequalities will be an n plus 1 on this side, and on this side, p over 3 will now be 2n plus 5/3, 2n plus 5/3. To be less than or equal to 2n plus 5/3 means you have to be at most 2n plus 1. Oh, shoot, there we go. 2n plus 1 minus n plus 1 leaves just n. Add 1 for the endpoints. And so the number in this case is n plus 1. I think I said the wrong thing here. P, in this case, p over 3. To say x is less than p over 3 means x is less than 2n plus 1/3, which means it's at most 2n. And now the difference is exactly n. All right. Whew. Okay. So primes that are one more than a multiple of 6. The number 3 will be a quadratic residue modulo such primes as long as that n is even. So in other words, you have p being equal to 12n plus 1. And primes that are one less than a multiple of 6, the number 3 will be a quadratic residue as long as n is odd. So that works out to actually being p being equal to 12n minus 1. There we go. So the quadratic character of 3 is plus 1 if p is one of those two types. And the other two types are, the quadratic residue of 3 is a negative 1 if p is congruent to, the other two possibilities are 12n plus 5 or 12n minus 5. All right, and that applies to the prime 3. That's why I was tracking it down over here. Thank you for figuring that out for me to get. So this is a mechanism that allows you to determine the quadratic character of any number using Gauss's lemma. You can manually compute all these triples and see what becomes small and what becomes large, or you can be a little systematic about it and actually figure out how you reduce a number modulo p. So I'm sorry I ended up using my time poorly there, but I will tell you that a variant of Gauss's lemma was developed by Eisenstein. It's now called Eisenstein's lemma. And it says that if you wanted to reduce these numbers mod p, deciding what's large and what's small, you can calculate that by using the division algorithm. I mean, you just take this big number and divide by p, and you keep the whole number part. If you subtract p times that from your original number, you'll get the residue mod p. So this floor function enables you to write out this idea of what it means to reduce the number mod p. Einstein's lemma allows you to pick up on that theme and rewrite the number a little bit. You only need to know whether it's even or odd, but it's the same idea. You run over all the small numbers and you start multiplying things by an a, and you look to see whether or not, or how much you have to round off. So I was going to use Eisenstein's lemma to finish the proof of quadratic reciprocity. I've gone way, way over today, and I apologize for that. But I can do that with you next time, and we'll have the full proof of quadratic reciprocity. It will enable us to get a mod p, the Legendre symbol a mod p, and compare it to p mod a. So that'll come on Wednesday. Alrighty, guys. Sorry about the losing track of denominator in there. I'll stick around in office hours if you want to continue this conversation a little more. Otherwise, we'll finish this on Wednesday.
See you on Wednesday.
Yep, see you.